Okay, welcome along. Another blurting video, this time on simple harmonic motion. So I've written out the definition. Acceleration is proportional to displacement and directed towards the equilibrium position. And the sort of thing we're talking about here is a pendulum that swings backwards and forwards, or a mass on a spring. So the key features of a pendulum are its length, mass on a spring, mass and stiffness of the spring, K. We've got that simple repeating motion, and I'll draw you a graph of that in a moment, and then we'll move on eventually and we'll think about what happens in periodic systems or forced oscillations where we apply force to an oscillator. So I think a good next point is to try and draw the graphs of how displacement changes with time, and then how velocity changes with time and acceleration changes with time. So that's displacement. So very important we understand the time for one complete oscillation is called the time period, which is capital T. The axis is lowercase t. That's just, how it changes with time. A is the amplitude, so that's the maximum value of the displacement. So X, the displacement is continually changing up to a maximum value A. Now I'm going to try and add a velocity time graph, so we know that the velocity is the gradient of this line. So it's got zero gradient here, zero gradient here, and zero gradient here. Here, it's got maximum negative gradient, so we need maximum negative velocity. Here it's got maximum positive gradient, so it's got maximum positive velocity. So that's what the velocity time graph looks like. We could do the same again for the acceleration time graph, but actually it's easiest just to mirror the displacement time graph, because it's just from the definition the acceleration is proportional to the displacement. Another way of saying it, towards the equilibrium position. It is directed towards the equilibrium position, which also means it's in the opposite direction to the acceleration. And let's just have a little look at that. So if we pull a pendulum, if we say this is the positive direction, we pull our pendulum back to here, so it's got a positive displacement. But the more we pull it that way, the more it wants to accelerate that way. So they're just always in opposite directions. Got some handy equations. The velocity of an oscillator is omega root a squared minus x squared. And if you want to know the maximum velocity, that occurs when x is 0, so we just get omega a. I suppose we should say what omega is. Omega is the angular velocity, just like we used in circular motion. So it's 2 pi f, which is 2 pi, f being the frequency, 2 pi over t. A equals minus omega squared x, and again you can see A is in the opposite direction to displacement because of the minus sign. Omega is the same value, and then A max is equal to we can ignore the minus sign now because we just want the greatest modulus, greatest magnitude. It's omega squared A, because the biggest possible value of x is A. And then finally I have the slightly more challenging x equals cos omega t. And the key thing here is our calculator needs to be in radians, because it's just an inherently radians process. We worry about the energy stored in oscillators, so we can plot a graph of energy against displacement. So we can put in plus A and minus A. So that there will be the kinetic energy, because the kinetic energy is a maximum in the centre where the displacement is 0. The potential energy is the other way around. That's a maximum at the edges, like a pendulum is highest at the edges and lowest in the middle. So that's EP. And then finally, That's the total energy. So E plus EK without any damping is a constant. Or, and this is slightly more tricky, if we imagine this is our displacement time graph, our potential energy is never zero. And if you think about our energy stored in a spring is a half F delta L, but F equals K delta L. So the energy stored is a half K delta L squared. Well, but delta L is just the same as X. So in other words, you just square that graph to get the potential energy graph. So we get a kind of trig function squared graph like that. And then the kinetic energy graph is just, and those two will add up always to the same amount. Finally, we've got forced oscillators. So often the equipment is we have a spring, a mass, a string, some kind of vibration generator connected to a signal generator, and we're imagining changing the frequency of our driving force and seeing how it responds. So the definition of a force oscillator is it's exposed to a periodic driving force like that. And then we can start thinking about how does that change with time. So how does the amplitude of the oscillations change with frequency? But a key variable here is damping. So you can kind of imagine putting a great big plastic disc on, or any other material. That disc is creating a lot of resistance. That means our oscillations would die away with time. So this is damped, this is undamped. Ignore the differences in frequency. So the damping is taking away energy and making the oscillations smaller, and you'll see why that's important in a moment. So we sketch a graph of the amplitude of the oscillations against the applied frequency. And a key thing to note is the natural frequency. So that's the frequency it most wants to oscillate at. So at a very low frequency, our oscillator's amplitude will be the same as the amplitude as the driver. And then when we hit the natural frequency, we get large oscillations, and this would be resonance. So when the natural frequency equals the driving frequency, we get large catastrophic oscillations. And then as we go to higher and higher frequencies, until eventually it really does come down pretty much to zero. And then we should say something about the phase difference. So these are over here in phase because they move together. These are out of phase, the oscillator and the driver. So that's 0 radians. And here the oscillator, the driver leads the oscillator by pi by 2 radians. Crikey, the autocorrect murdered that, didn't it? Why is my rubber not well? Here we go. So we'll have another go at writing pi over 2. Oh, that's survived a lot better, hasn't it? If we increase the damping, this effect becomes less and less. Okay, so that's more damping going down. So if you get a question about how do we get rid of the resonant behaviour, often the answer is damping. So I think we'll call that a day there.